This is part 4 lecture of the series on endocrine control, endocrine glands. For this video, I'm going to cover the pancreas and the parathyroid glands. These are two endocrine glands, or at least for the pancreas, the endocrine portion of the gland, that deviates from some of the other glands that we talked about in that they're not necessarily controlled by the hypothalamus/pituitary system. So these are going to be directly stimulated by the mineral that they're trying to regulate, mineral or nutrient molecule that they're trying to regulate. So we're going to jump into the pancreas first, and then we'll cover the parathyroid glands. Okay, let me turn on my laser. Here we go. So again, if you recall from the digestion lecture, we looked at the pancreas there, and the pancreas has a dual function. In the role with digestion, most of the cells that are associated with the pancreas are called acinar cells, and they have an exocrine function. So what they do is they secrete digestive enzymes and sodium bicarbonate into the duodenum in order to facilitate digestion in that area. In this lecture, we'll be talking about its endocrine function. So this is the function where it's able to secrete hormones. And these two hormones that we're going to talk about don't have to do with digestion. They actually deal with the effects after absorption that comes from the materials broken down during digestion. And so what you want to consider is that, remember that in physiology, our bodies function at the cellular level. It's the cells that are doing work, doing chemical reactions, catabolizing some materials, meaning breaking them down, or using anabolism to build up materials, right, for things that we need. Well, in order for that to function, we need nutrient molecules to do that. So the cells need a continuous supply of nutrients to perform these actions. And instead of us then having to eat continuously, what we can do is we can eat large quantities of food, and then when we break it down through digestion and then absorb it into our bloodstream, then the cells can use these nutrients directly from the bloodstream, but then eat additional nutrients, excess nutrients that we take in, we can store it in other areas of the body. So that way, during periods in between meals, as it says here, then we can access those stored supplies. We just, through catabolism, break them down once again into their monomers and release them back into the blood. So again, our food intake is intermittent. So then we store those excess circulating glucose molecules, fatty acids, and amino acids. Okay. And so a couple of terms to remember that we store these metabolic fuels during what's known as the absorptive state. That's the state that occurs right after eating a meal. I'm going to show you on the next slide that's when we absorb through the intestines. And then during the post-absorptive state is when we can mobilize that those stored nutrients. So post-absorptive state is what occurs in between meals when we're not eating. We're not replenishing our blood with nutrients. So we need to do that with the stored molecules. Now, most of the cells in our body can access the stored molecules, and they can use some of the metabolic fuels that are other than glucose. We can use fatty acids, we can use amino acids, but the brain, I want to call this out, has to continuously be supplied with glucose. And that's its sole source of energy. So we're going to see a little bit different situation going on with the brain. We do things in order to make sure we have glucose available for our brain at the expense of some of our other organs. Okay, so this is a nice graphic that's in your book. So this really links together the digestive phase with that metabolic fuel use and storage. And so again, we eat proteins, carbohydrates, and fatty acids or triglycerides, fats, lipids. And when we do that, it goes through the digestion because these molecules are too large for us to absorb into our bloodstream. So digestion is that property where we break down each of these into their component parts. Proteins become amino acids, carbohydrates mostly become glucose, and triglycerides become fatty acids and monoglycerides. These are the molecules that are what we call absorbable. We can absorb them either from the intestines directly into our bloodstream, or in the case of lipids, it goes from the intestines into the lacteals from the lymphatic system, which then can help bring it into the bloodstream. Okay, so that's what's referred to as the absorptive state. Okay, and again, uh, everything goes into the bloodstream, and we can have a direct access of these monomers to the cells in our bodies so that they can do the work that they need to do. So, for example, amino acids will go into our muscle cells where they can build them back up through the process of anabolism, excuse me, to make proteins. Okay. Then we can also, again, put them directly and use them as metabolic fuels into our cells. Amino acids can go into the Krebs cycle. Glucose will start with glycolysis. Fatty acids as well can go into the Krebs cycle. However, again, when we eat a meal, much of this is in excess and our cells can't use it up right away. So what we want to do is store it. So we might take our glucose and build that up into a product called glycogen. That's the storage form of glucose. And that happens in the liver, mainly in the liver, but also our skeletal muscles do that as well because our skeletal muscles need such a large supply of glucose. They actually store it right in their own organ so they can have access to it. And to get access, then we would take glycogen and in the process of catabolism, C-A-T, catabolism, break it down back into glucose, right? Triglycerides, fatty acids, can be reformed back into triglycerides in our adipose tissue, and then when needed, broken back down into fatty acids. But notice that amino acids can be converted to fatty acids. Amino acids can be converted into glucose. Glucose can be converted into fatty acids, so on and so forth. So we have this means of storing. So what we're going to look at is then how does these two hormones, insulin and glucagon, regulate? We'll look mainly how it regulates glucose, plasma glucose levels, so that we always make sure we have some available to our cells. Here's a table that I would like you to review. Hopefully you went through some of this in general biology, but we're going to be using these terms. So I just mentioned on the previous slide that we can take glucose and through anabolism create a larger molecule, storage molecule of glycogen. Well, that's a process called glycogenesis. And that occurs in the liver. And so that's a process of taking glucose out of the blood and storing it in the liver in the form of glycogens. So the overall effect is decreasing the blood glucose level. Okay, well, we can do the liver actually can do a process called glycogenolysis. And then that's the opposite process. The liver can take that glycogen and break it back down into glucose and release it into the blood. So that would increase blood glucose levels, right? Gluconeogenesis is the process of taking amino acids and converting those into glucose. That would raise blood glucose levels. right? Protein synthesis, we can take those amino acids and make them into proteins, right? So that's anabolism. That would decrease blood amino acid levels because, again, we're pulling it out of the blood and the cells are using them to make proteins. Okay. So forth and so forth. Same with lipogenesis is taking individual fatty acids and glycerol and making triglycerides, and then lipolysis is breaking down those triglycerides into fatty acids and glycerol. Okay. So these are our main energy sources. And again, you can see what that does to the level of those nutrients in the blood. And then we do have other means of using lesser energy sources. These are usually, we use these sources during generally a starvation phase. So we can actually take glycerol, lactate, and something called ketone bodies and use that for energy. But again, that's usually in an extreme state. Okay, so back to the pancreas and what we call fuel metabolism, how we control that amount of fuel that's available in our bloodstream. Okay, so really there are several hormones that can actually control this. I talk a little bit about this at the end of this segment. So again, several hormones can control the blood nutrient levels via the stimulation of anabolism or catabolism. But I'm mainly going to focus on these two hormones from the pancreas called insulin and glucagon. So first, let's take a tour of the pancreas. You can see it's that gland that lies just below and behind the stomach. And as I mentioned in the digestive function that it has, these cells that are more numerous all around, these are called the acinar cells. And again, they secrete the digestive enzymes. The cells that are also associated with them secrete the sodium bicarbonate that travels along this duct and gets released into the duodenum to help with the digestive process. The hormones, however, are created by other cells in this pancreas. They're usually clustered in these little sections here, and these are called the islets of Langerhans. Islets of Langerhans, sometimes just called pancreatic islets. And these are the cells that have an endocrine function. So they create signaling molecules that get released into the bloodstream and affect other cells away from the gland. And so again, by definition, those signaling molecules are hormones. And it's mainly insulin and glucagon. So within the islets of Langerhans, you have cells referred to as beta cells. These are like the purple ones here. That's what makes insulin. Then you have alpha cells, usually around the periphery. That's in green here. Those are what secrete glucagon. And then you also have cells called D cells. That's these here. Those are from, it's called D cells because they're delta cells. They release a molecule referred to as somatostatin, and somatostatins help regulate the digestive system. In fact, as digestion is progressing and we're getting to the end of it, somatostatins help to inhibit then the digestive glands, the digestive cells, which would then slow down digestion. It'll then end up inhibiting the absorption of nutrients in order to prevent an excessive amount of those nutrients in the plasma levels. So somatostatins have a lot of jobs there, but again, so it's more about, it indirectly can control nutrient absorption because it's helping to control the digestive system. Okay, but again, we're going to stick with insulin and glucagon. And I just want to make a note, this is not anatomy, so you will not see a picture like this. I will not ask you to identify beta cells and alpha cells, but this is physiology, so you will have to tell me the function of beta cells and alpha cells and delta cells and possibly acinar cells. We'll get a review of that as well. Well, they function in digestion, so for sure you'll need to know that. Okay, so insulin secretion from the beta cells. So the job of the hormone insulin is it lowers blood glucose levels, fatty acids, amino acid levels, and promotes their storage. So the stimulus for insulin is an increase in blood glucose levels. Though the increase in glucose levels will directly act on the beta cells, causing those to secrete insulin. Now, the way it does it, I'm not requiring you to know it, but it's just interesting to note that the presence of glucose at the beta cells actually causes, in a series of events, causes a change in the membrane potential, which then causes the beta cells to release insulin. I just want to mention that because we have learned that membrane potential changes really only occur in the muscle cells and neurons, and this is one incidence where it occurs in a cell outside of those two groups. It probably happens in other areas of the body, but it isn't well understood yet. So I just wanted to make that observation there. It's kind of interesting. So again, I want to say again, the stimulus for insulin release from the beta cells is the presence of glucose in the blood, or a higher level of glucose in the blood. It isn't the hypothalamus stimulating the pituitary gland, which then releases a hormone to stimulate the pancreas. So that's not what's occurring here. And that's why I wanted to separate this organ from some of the other endocrine organs that we talked about. Okay, so here's again what happens. Anything that will lower blood glucose levels, either directly or indirectly, will is what insulin will cause. It will either stimulate a process or inhibit it. So let me show you here. So I put this table back up for glycogenesis, which again, it was the taking glucose out of the blood and converting it to glycogen in the liver. Insulin promotes this process. Insulin promotes glycogenesis. So again, the consequence is it will end up lowering blood glucose. That's the job of insulin, lowering blood glucose. So glycogenolysis, its job will increase blood glucose by converting glycogen back to glucose. So insulin is going to inhibit glycogenolysis. Gluconeogenesis is converting amino acids to glucose. That raises blood glucose levels. So that's going to be inhibitory. Okay. Protein synthesis would decrease amino acid levels. And again, remember, amino acids can be converted into glucose. So if you decrease the amount of amino acids, then that will decrease glucose. So therefore, insulin promotes protein synthesis. Okay. Protein degradation, and protein is degraded into amino acid. Well, that would release more amino acids into the bloodstream, and that would inhibit insulin. And so therefore, insulin would inhibit protein degradation. Okay. Fat synthesis, that's the action of making fatty acids and glycerol into triglycerides, right? That would end up decreasing blood fatty acids. Blood fatty acids can be converted into glucose. So again, you decrease the overall level. So that would prevent glucose from being formed. So insulin, what do you think it would do? Inhibit or promote this fat synthesis? Well, it would promote it. Okay. And finally, the opposite is true. If you're going to increase blood fatty acids by breaking triglycerides down into fatty acids and glycerol, then insulin would inhibit that process. Okay. So this is the difference between memorization and learning. Okay. It's going to be very difficult to just memorize this table. If you try to just memorize this table, you might be able to do it, but when you get nervous on the test, you may mix this up. But if you remember what these are, remember genesis is the creation of something. So we're making glucose and we're building it up into glycogen. Okay. If we're doing that, that happens in the liver. That means we're converting glucose into something else. So that's going to decrease a blood glucose level. The memory then comes in, insulin decreases blood glucose level. So if you know glycogenesis decreases blood glucose level, and you can figure that out, then you should be able to apply the fact that insulin promotes glycogenesis, right? Lysis means to break down. Well, if you're breaking a big molecule down in a smaller molecule, then you're releasing more of that product into the blood. So that would raise glucose levels or other substances that could be converted into glucose. So insulin is going to inhibit that process. Okay. All right. This one you got to remember, gluconeogenesis. That is making amino acids into glucose. So that raises glucose levels. So again, insulin is going to inhibit that. That's the way that you use this. Okay. So again, the overall effect, insulin lowers blood glucose levels. And it does so by promoting the cells in your body everywhere to uptake glucose so they can use glucose directly. But then it also either promotes or inhibits these actions of storage or release of storage. So it promotes the action of storing glucose, and it inhibits the action of releasing glucose. Okay. Oh, I forgot. I circled this here because again, this consequence that really can tell you whether insulin promotes it or inhibits it. Okay, we want to lower blood glucose levels. Okay. So again, have it there again. Insulin lowers blood glucose. And I just want to stress again, the primary stimulus for beta cells in the pancreas to release insulin is the increase of the blood glucose levels. That's the primary stimulus. It's not coming from the brain, the hypothalamus, or anything like that. It is a direct action of an increase in blood glucose on the beta cells in the pancreas. So they release insulin. Okay. And that's the direct negative feedback system, okay, between beta cells and the concentration of glucose. All right. So here again, this nice little chart shows you that glucose absorption from the digestive tract, that's going to increase glucose, right? That's going to cause the increase of glucose in the blood, which would then cause the release of insulin, which then causes cells to take up glucose, put it into their cells, and again, to use for energy. And the way they do that, insulin, once it binds to a receptor, it actually causes the establishment of these glucose transporters into the cell's cell membrane. So now glucose can move in on its concentration gradient. Okay. Here, again, hepatic glucose production, that presence of insulin then can stimulate the liver to break down or to take up glucose and form it into glycogen. That was that process of glyconeogenesis. Oh my goodness. There we go. To create it, glycogenesis. There we go. Stumbled on my words. My dog was poking at my hand down here. Right. So here, hepatic glucose production, this is what would increase blood glucose, and that's glycogenolysis. So again, taking the stored glycogen and breaking it down into glucose. That's going to raise it. These are things that decrease blood glucose levels, again, taking it into the cells. And then, again, if there's way too much glucose, then we would excrete glucose through the kidneys, through the nephrons, through urine. But this only occurs if we've gotten into the disease state, okay? And we're going to talk about that in just a second. But I wanted to put this flow chart in here again, just to drive home the direct route of stimulating insulin secretion in order to lower blood glucose, blood fatty acids, blood amino acids, but to increase protein synthesis and other fuel storage. And that direct line is we eat food, right, through digestion and absorption, then we increase our blood glucose concentration. That has a direct effect on the islet beta cells in the pancreas, so we increase insulin. But remember that we always have external forces as well. So parasympathetic control can actually act on the beta cells, which would increase insulin. Okay. Sympathetic stimulation, along with the hormone epinephrine, can have a negative effect on the beta. So it would decrease insulin secretion, right? Gastrointestinal hormones. So as those hormones are being secreted, then what that is, it acts like a feed-forward system to the endocrine portion of our pancreas to say, hey, food's about to come. And so if food is about to come, it makes sense to prime our blood and increase the levels of insulin so that by the time the glucose hits the blood and starts to increase, then insulin can cause the immediate movement of glucose into cells to prevent that blood plasma spike. Okay, very important for us to prevent that. Okay. So that's how insulin would normally work in our bodies. If we don't have the ability to take up glucose we're going to go through the reasons right now, we could get a disease referred to as diabetes mellitus. Again, diabetes mellitus is because we have too much glucose in our plasma. Okay, and that can be caused for two reasons. If you have type 1 diabetes, it's due to a lack of insulin secretion. This is usually because of an autoimmune issue where T lymphocytes are attacking the beta cells and it's destroying them, so they don't have the ability to release insulin. Okay. Type 2 diabetes has to do with an increase, usually lifestyle choices, an increase in eating too many carbohydrates. But there's also thought to be a genetic component to this as well. Maybe not being able to deal with the carbohydrates for other reasons that we don't understand yet. And so what happens is type 2 diabetics do have the ability to create and release insulin, but with the abnormally high levels of glucose in the bloodstream, what happens is there tends to be then a constant secretion of insulin. And the more often a signaling molecule bombards other cells, those cells begin to do what's called down-regulating. They want to ignore insulin. They start to move their receptors out of there because it's too much going on. So then if you remove those receptors and you're not responding to insulin, then you're not taking the insulin out of the blood, and that leaves you with a high amount of glucose in the plasma. So both type 1 and type 2 diabetes, although they're caused by different things, they end up causing the same problem, which is hyperglycemia. And so with hyper to a lot, glycemia, glucose in the blood, that means that that's going to eventually get filtered by the kidney. And remember, with a regulated amount of glucose in the blood plasma, that the kidney is able to handle that amount of glucose, and the nephron will reabsorb all of the glucose filtered back into the bloodstream at the proximal convoluted tubule. And so remember, the amount of transporters that do that we referred to as Tmax. But when you're hyperglycemic, because of either type 1 or type 2 diabetes, then glucose stays in the filtrate. Those glucose transporters are occupied. They're too busy while more glucose is coming in. So that fluid keeps flowing and it bypasses those transporters. And once the filtrate leaves the proximal convoluted tubule, it doesn't have the opportunity to get reabsorbed because the rest of the nephron doesn't have the glucose transporters to do that. So that leaves glucose in the filtrate. And so that makes the filtrate hypertonic to the surrounding tissues. That means that the filtrate's more hypertonic than the surrounding tissues, then less water can be reabsorbed. Okay. And so with less water being reabsorbed back into the bloodstream, then that means we have an increased urine output. So that's one of the signs that a person is diabetic. You might find an increased urine output. Therefore, if you're not able to reabsorb water and you're releasing a lot of water through the urine, you might be thirsty. The body's trying to replace that water. So it's signaling you to be thirsty to drink more water. So that's another symptom of diabetes. Diabetes mellitus, diabetes literally means to flow through. So that's referring to the increased urine output. Mellitus means sweet. And so that refers to the glucose in the urine. There's another form of diabetes called diabetes insipidus. And insipidus means tasteless, no taste, tasteless. Okay. And so again, it's a situation where there's a lot of urine output, but there's no glucose in it. It's not sweet. That has to do with not being able to produce enough antidiuretic hormone, also known as vasopressin. So that's a different process here, but the result is the same. This was named again for the glucose presence or no glucose presence. And the way they used to figure this out before we had a test for this, doctors would actually taste the urine if they suspected a form of diabetes and wanted to know which one it was. Mothers might even do this if they noticed their children had an increased urine output, they might actually taste it. So we don't have to do that anymore. No tasting urine anymore. Okay, so be able to relate diabetes mellitus to the effects of insulin or the lack of insulin, understand type 1, type 2 diabetes. Relate that then to hyperglycemia, and then you can relate hyperglycemia to the actions in the kidney and why we end up with an increased urine output. So your answer should include what happens at the proximal convoluted tubule with Tmax. And this got explained in more detail in the urinary system lecture. Okay. Okay. Now, there is a condition called hypoglycemia. Hypoglycemia can be caused by an excess of insulin. So again, low glucose in the bloodstream. And excess insulin can mainly be caused by two things. One is if a diabetic patient who takes insulin injects themselves with insulin, if they inject too much insulin, then that can cause too much glucose being taken out of the blood, and you can go into insulin shock. The second reason for hypoglycemia or an increase in insulin, excess insulin, is what's called reactive hypoglycemia. And this can happen in non-diabetic individuals. Their beta cells have an over response to the presence of glucose, and they end up over secreting insulin. And therefore, then the cells take up too much glucose out of the blood. This is kind of difficult to diagnose. It isn't really sure known why. But one of the issues, if you have an excess of insulin, then that can really have an issue with your brain. Sorry, you might hear my dog barking. Because remember, the brain needs a continuous supply of glucose. And while the glucose uptake by the brain is not insulin dependent, it is plasma glucose level dependent. So with an excess of insulin, it's overall lowering too much the amount of glucose in the plasma. And then therefore, there's not enough glucose in the plasma to feed the brain. And so this might be referred to as brain starving hypoglycemia. And again, sometimes we might notice symptoms, just other things, being lethargic, not being able to think well, could be other muscle control issues because the motor system isn't working correctly. So sometimes, we see other symptoms that indirectly point to this. Okay, so insulin secreted from the pancreatic beta cells lowers glucose. When glucose levels fall down toward the lower limit of homeostasis, then that takes that signal off the beta cells, and beta cells will start to slow down their secretion of insulin. However, glucagon is another hormone coming from the alpha cells of the pancreas, and glucagon will increase, or the alpha cells will increase their release of glucagon, and glucagon in general opposes the action of insulin. So it will do things that will increase the amount of glucose in the bloodstream. Okay, so again, we start to see glucagon increase its rate of secretion during that post-absorptive state when we haven't eaten a meal in a while. It takes about 4 hours after eating a meal for all the absorption to stop. So 6, 7, 8 hours into it, if you haven't eaten, we're using the glucose out of the blood. So while that's going down, then that will trigger glucagon to secrete. And then that's going to work on the target cells are mostly in the liver to do things to release that stored glucose. Target cells are also in the adipose tissue, again, to release the glucose that's been stored in there as fat. Okay. So what else do I want to say? So again, so insulin and glucagon work as a team in order to maintain blood glucose levels. So as one is high, the other's low, and then as blood glucose levels shift, the hormones will also shift as well. All right. And this picture shows that really nice. So this is like the islets of Langerhans. You got your alpha cells around the periphery, the beta cells in the middle. So here you can see as blood glucose levels increase, that stimulates the beta cells, that presence, right? Direct stimulation on the beta cells to increase insulin, which then ends up lowering blood glucose levels. And you saw that chart, which shows how it lowers blood glucose levels. You should know that. Okay. That increase in blood glucose levels, though, can have a negative effect on the alpha cells. So that's what partially keeps glucagon levels low. Okay, but as the blood glucose levels lower and return to normal as a result of insulin, then that low blood glucose, right, as it starts to get lower than homeostasis, then that stimulates the alpha cells to ramp up their release of glucagon. And again, those effects of glucagon will raise glucose levels back to normal. So you see the opposite effects that it has there. Okay. And so I redid this table. So now you can see the effects that glucagon has. Okay. Glucagon raises blood glucose levels, fatty acids levels, amino acid levels, and whoops, I gotta erase it. That's a mistake. It reverses their storage. Okay, I didn't change enough on the slide. So make sure you see on the slide that it doesn't promote storage. It actually depletes the storage. It wants to release that stuff. So what you see here in the table is correct. So glycogenesis, which was converting glucose to glycogen, the presence of glucagon then inhibits this process, right? So if it's inhibiting um, the lowering of blood glucose. So that's going to reverse this arrow. It's going to raise it, right? Glycogenolysis, that's converting glycogen to glucose. So that's something that will raise blood glucose levels. So glycogen is going to promote that, right? Converting amino acids to glucose, that's called gluconeogenesis. So glucagon is going to promote that, right? That's going to raise, it wants to promote raising blood glucose levels. But amino acids converting that into protein, that means we're taking the amino acids that could be converted to glucose and we're storing those as protein. So we want to inhibit this lowering of amino acids. So glucagon inhibits this process. Okay, but breaking down or using catabolism to break down protein into amino acids, that would raise blood amino acids levels. So then glucagon would promote protein degradation. Okay, so on and so forth. So I'll let you go through that and try to understand that. Okay, so there's really no known disease caused by glucagon deficiency. But it is known that glucagon, an excess of that, can actually aggravate the hyperglycemia of diabetes mellitus. So really think about this. So, and I want to be careful because this is hard, this is easy to flip. So I want to make sure I say this correctly, because diabetes mellitus is usually accompanied by glucagon oversecretion, right? So diabetes mellitus is an inhibition of insulin secretion, but it is accompanied by a glucagon oversecretion, because when glucose enters the alpha cells, then normally it would inhibit glucagon secretion. But what's causing that glucose entering the alpha cells is the presence of insulin. So if there is an insufficient insulin, then this process of inhibiting glucagon would be inhibited, right? So therefore there's an increase in glucagon, which then increases glucose levels. Okay, so it's almost a positive feedback going on there. So diabetics, again, frequently have this high rate of glucagon secretion concurrent with their insulin insufficiency. So oftentimes in conjunction with the insulin therapy, injecting insulin into the bloodstream, it might go along with something called somatostatin therapy, because somatostatin can inhibit glucagon secretion. So having those in conjunction can really help control blood glucose levels for people with diabetes mellitus. Okay. Rewind that if you need to hear that again and again in order to understand that. But again, I did mention that other hormones can control glucose homeostasis, epinephrine, cortisol, growth hormone. So we've been through these in the other lectures on endocrine. So whatever I said in those other lectures, that's all you need to know about this. I'm not adding anything to that in this lecture. So please go back to those previous lectures. I will show you this table that's referred to as here. So I like this table because it has a really nice summary of the effects of insulin and glucagon. You can read across here. But then it does summarize epinephrine, cortisol, and growth hormone. Again, I'm not adding anything to the previous lecture, but read through this, whatever corresponds to the previous lecture, you can go with. Anything that's extra here, I won't test you on. Okay, and then finally, while I did say what the processes we went through in the control of insulin and glucagon release is the direct stimulation of glucose levels of the blood and not the stimulation of the hypothalamus, I do want you to know that the hypothalamus can play a role in controlling glucose homeostasis, and mainly because the hypothalamus does have the ability to sense blood glucose levels, and it may then have an effect directly onto the liver. But again, that's not the process that we were discussing here. So I want to make sure you understand that direct process. Okay, that's it for the pancreas. So we want to move on to the parathyroid glands and how they control calcium metabolism, right? So this is a mineral that's being controlled, and we have seen the control of sodium and potassium concentrations in the ECF controlled by a hormone called aldosterone. That was in a previous lecture. So now another mineral, calcium, is controlled by mainly the parathyroid gland is the main controller by the hormone called parathyroid hormone. So it's the same name as the gland, often called PTH for hormone. It's not in there. PTH for hormone. And I want to stress that controlling the plasma levels of calcium is very closely regulated, because think about all our past work in physiology so far. Think how many times you saw the role of calcium in the nervous system, in the muscular system, all three muscle types, right? And so calcium is so essential in these activities. Calcium, I mentioned that the release of insulin is actually the result of a change in membrane potential, and calcium is actually important in the exocytosis of insulin, just like we saw with neurotransmitters. So the point is, if our calcium levels go out of whack, it could mean death. And so we have to, our body is very careful in controlling the plasma calcium levels. Okay. So again, in both the calcium homeostasis and the balance of calcium, okay, it depends on the hormonal control of exchanges between the ECF, right, interstitial fluid and plasma mainly, and the bone. So what we're going to see in a minute, we'll talk about it in just a minute, is that bone is the main storage of calcium. And so we actually obtain calcium from our bones. Okay. We also can prevent calcium loss from our kidneys. And then we also control calcium absorption in our intestines. All of these things help to raise plasma calcium levels when it starts to fall. And all of this is an attempt to avoid something called hypocalcemia, right? Hypo, low, calcium, emia in the blood, low calcium in the blood. Okay. Three other hormones, or actually three hormones, control calcium. Parathyroid hormone is the most important. Then we'll look at the effects of calcitonin from the thyroid gland. And then we'll also look at the effects of vitamin D, which is synthesized in the skin, and it is actually a hormone. But again, let's look at parathyroid hormone first. So the parathyroid glands are the main controller of calcium metabolism. So where is that? So we're looking at the back of a person. We can see the back of their trachea here. Remember, the thyroid gland wraps around the front of the trachea, has a little opening in the back. So if we look at the back of the thyroid gland, these 4 nodules, those are the parathyroid glands. Okay. And again, their job is to release parathyroid hormone. Here it is, PTH, parathyroid hormone. It is a peptide hormone. Okay? And again, its job then is to raise the free plasma calcium. And this could have a life-saving effect. Again, if our calcium levels fall too low, if we get into hypocalcemia, again, think of that. We won't be able to contract muscle. Well, the heart won't contract properly. That's bad. All the contractions of our vasoconstriction and in our digestive system and things like that, that wouldn't work. That could kill us, right? Even skeletal muscle, because your diaphragm is skeletal muscle. Okay. And so if you can't contract your diaphragm, you won't be able to breathe. So this is really important that we regulate this very closely. So 99% of calcium is found in our bones. All the calcium in our body, 99% of that is in our bones at any time. And so our skeleton is considered a storage area for calcium. And bone continuously, just naturally undergoes remodeling. So it's remodeling means this constant process of depositing bone, creating it, and breaking it down, or what's called resorption, right? And so it's just constantly remodeling for a couple reasons. One is to, as you grow, and then even as an adult, your body changes and shifts, your skeleton kind of keeps up with that. So it's a more appropriate scaffolding as your body is changing. Okay. And then the other reason, again, is to store calcium and be able to use it when we need to. Okay, so let me just remind you a little bit here. So bone, remember that bone is a hard material and it's hardened by structures referred to as, or substances called hydroxyapatite crystals, right? Hydroxyapatite crystals. Remember that from anatomy. And so hydroxyapatite crystals is mostly consists of calcium phosphate salts. Okay, so again, blast from anatomy, there are 3 cell types in bone. The osteoblasts are the parts of the bone that function, the cells of the bone that trap calcium and phosphate and form bone. And then once it does, it forms it in these rings. And so the osteoblast, once it's caught in the osteons, it becomes an osteocyte. And the osteocyte now can just maintain the bone that's surrounding it. But then osteoclasts can come along and they can secrete hydrochloric acid, which ends up breaking down the bone, releasing the calcium and the phosphate into the plasma. Okay, so this constant opposing actions of osteoblasts and osteoclasts, that's what remodels bone. Okay, again, going here, depositing bone by the osteoblasts or resorbing bone by the osteoclasts. Okay, so parathyroid hormone is going to act on these cells and move calcium from the bone into the plasma. Okay, so again, this is not anatomy. I'm not going to ask you about lamellae and osteons and all of that, but you should remember the function of osteoblasts and osteoclasts and their opposing mechanism. Okay. Okay. So, other thing to remember about bone is that the mechanical stress favors bone deposition. What is mechanical stress? That means putting pressure on your bone. Anytime that you lift something heavy or you are running or, again, have that impact on your bone is what I'm trying to say. That then increases bone to increase. That increases the osteoblast capacity to increase the mass of the bones, and it causes them to strengthen. The opposite of this, of mechanical stress, or the lack of mechanical stress, will weaken bones. So like astronauts, when they go into space, they will come back with more weakened bones because they don't have any gravity to be able to cause that impact against their bones, right? We also know that age affects bone density. And so when you're young and you're growing your bones, and then up to about through your 30s, your depositing of bone outpaces the breaking down of bone. So in your 30s is when your bone density is at its peak. By your 40s, it starts to decline, okay, the bone density. You can keep up the bone density, though, by increasing the mechanical stress. And I'll tell you, as you get older, you tend to not want to be as physically active, but that's the time when it's most important to be physically active, because then the mechanical stress, again, can stimulate that bone deposition. Then you can prevent what starts to happen in your 40s and 60s, or I'm sorry, 50s to 60s. The bone resorption can start to outpace the bone deposition. So again, that's why exercise is so important in your older years, so that you slow that process down. So when the bone resorption outpaces bone formation, that's a condition called osteopenia. Okay. If osteopenia is allowed to continue for a long time, then eventually your bones become very porous, because that breakdown, the bone is just going away, and they become very weak, and then that's osteoporosis. So again, the real underlying causes are uncertain right now, but we do know with postmenopausal women, you're not producing as much estrogen, and estrogen preserves bone. And so really postmenopausal women really have to be careful about this. Okay, so I just kind of wanted to add that in there. So, so in a normal situation, though, when we're using up plasma calcium, remember, like the heart cardiac muscle, it's going to pull calcium from the plasma, from the extracellular fluids. So again, plasma levels for these normal processes will go down. So this is normal processes. Parathyroid hormone will be stimulated to be released. Again, it's the lowering of blood calcium levels that stimulates the parathyroid gland to release PTH, not the hypothalamus or pituitary gland. And what that does is it withdraws calcium from the calcium that's stored within the fluid portions within the bone. Okay. So it just transfers calcium, what we call the bone bank, the calcium that's stored within the fluid portion of the bone into the plasma. Okay, and so therefore it's not breaking down the mineralized bone, it's only transferring calcium into the plasma. Okay, so that's important. So again, under normal circumstances, when calcium levels in the plasma falls to the lower level of homeostasis, so we're not in a critical position, it's just falling in the lower level due to normal processes, parathyroid gland will be stimulated by that lowering of calcium to release parathyroid hormone. That acts on the bone. It's inserting transfer proteins and things you don't need to know. Your book goes into it in more detail, but I'm not asking you to know that detail. But what I want you to know is that what it's doing is it's causing the removal of the calcium from the bone fluid and directing it into the plasma. So this is not breaking down mineralized bone. Okay, so that means it doesn't diminish bone mass. Okay, Normal situation there. Now, what if you have a situation where we have what's called chronic hypocalcemia? Okay, low calcium in the blood chronically means it's over the long term. So its chronic effect or its long-term effect, this hormone, parathyroid hormone, is to promote the localized dissolution of bone in order to release calcium into the plasma. This is breaking down bone. Okay. How does it do that? You might think, well, parathyroid hormone must stimulate the osteoclast. Only indirectly. So here's how osteoblasts and osteoclasts work. Remember, osteoblasts build bone, while osteoclast breaks down bone. Okay. Again, normal process is we're constantly doing that, building and breaking down bone in order to remodel our bone. You remodel your entire skeleton about once every 10 years. Completely new skeleton, right? It just takes that long to get through everything. Okay. So osteoblasts and osteoclasts, though, need to be in communication so one doesn't outpace the other, right? So osteoblasts take that role. Osteoblasts, as it's building bone and it starts to outpace osteoclasts, then the osteoblasts will secrete a paracrine known as rankle. And rankle then stimulates the osteoclasts to ramp up their ability to break down bone. So again, it just prevents us from depositing too much bone. Okay, so that's the balance. But what parathyroid hormone does, when we're in a situation of calcium being too low for long periods of time, okay, long-term low calcium in the blood, hypocalcemia, stimulates its target cells, the osteoblast, stimulates it to release rankle, which stimulates the osteoclast to break down bone. This then does break down bone. It releases both calcium and phosphate, because remember, calcium phosphate is attached to one another in the hydroxyapatite crystals, right? So both of those get released into the plasma. Now that both of those are in the plasma, though, that's going to automatically go to the kidneys. Your blood flows by the kidneys to get filtered. So PTH will also act on the kidneys to cause the kidney, the nephron, to reabsorb calcium back into the bloodstream. So it conserves the calcium. It doesn't allow it to get flushed out in the urine. So parathyroid hormone not only acting on the osteoblast as the target cell, but it acts on the target cells within the nephron to reabsorb calcium. So we conserve the calcium. But it doesn't do anything to conserve the phosphate. It allows the phosphate to be eliminated with the urine. And here's why. As long as calcium is in the blood plasma with phosphate, phosphate is going to want to attach to it and draw it to the bone, which would then decrease our calcium levels. It would only promote this hypocalcemia, right? So parathyroid hormone, by acting on the kidneys, again, conserves the calcium, but removes the phosphate. Okay, and that allows the calcium levels then to increase in the blood plasma. So only under extreme case of hypocalcemia does parathyroid hormone actually get calcium by dissolving bone. Under normal circumstances, parathyroid hormone can raise plasma calcium levels within the homeostatic range by withdrawing calcium from the calcium that's just in the bone fluid and not associated with the scaffolding of the bone, okay, or the crystallized portion of the bone. Okay, rewind that to make sure that you understand the differences there. Okay, all right. The other effects of parathyroid hormone, because we mentioned that calcium, we get it from our diet, and so it needs to be absorbed in the intestines. So when calcium levels go down, parathyroid hormones target cells can also be in the intestine to promote the absorption of calcium and then also phosphate levels, right? And that's going to help build bone. Okay. I'm sorry. I said that incorrectly. I said that the target cells are in the intestines. That's not true. It actually, the target cells are in the skin that helps to activate our vitamin Ds, okay, which is a hormone. The vitamin D then, with that increase, will help the absorption of calcium, okay? So again, and here was the key, indirectly, okay? So it's not acting on the intestines where absorption takes place. It's indirect. It's acting to activate vitamin D, and then the vitamin D acts on the intestines to help with the absorption of calcium and phosphate. Okay. Um, so vitamin D is a very important hormone in our body. It is made in our skin. So it was labeled a vitamin because we thought it was a substance that we could only get externally and through our food, which we can drink milk and things like that. Leafy greens gives you vitamin D, but it does get synthesized in the skin when we are exposed to UV light from the sun. And but you're thinking, but UV light causes cancer, right? So we need a certain amount. You just need a small amount, 5 or 10 minutes in the 5 or 10 minutes in the sunlight can help increase your vitamin D absorption, and that's all that you want. Let me pause for just a moment. I need to plug in my laptop. So again, vitamin D is very important. And a lot of Americans' levels of vitamin D are low, especially in women. And so it's a really good idea when you go to the doctor and you get a blood test that you ask them to check your vitamin D levels. It can really save you in the future. Again, so the primary regulator of parathyroid hormone is the level of plasma, the concentration of calcium within the plasma. Again, that's the primary regulator. It's not the hypothalamus, anterior pituitary. So again, the effects of parathyroid hormone in all cases is to increase calcium level concentrations, okay? We have this other hormone, we mentioned calcitonin. So calcitonin is a hormone that's released from the thyroid gland, and it lowers plasma calcium concentrations. So again, under normal circumstances, when we're not at any extreme, parathyroid hormone is the main regulator of calcium. Calcitonin only comes into play when we have way too much calcium in our system, right? And so it can lower calcium movement from bone fluid into, or decrease that movement of calcium from the bone fluid into the plasma, right? And so it's just kind of inhibiting the effects of parathyroid hormone in the normal situation. Long term, it can actually inhibit the osteoclasts. So remember, osteoclasts break down bone and release calcium into the blood. So calcitonin can actually inhibit that. And so you kind of see that, just like we saw with insulin and glucagon, the same with parathyroid and calcitonin. As plasma levels of calcium goes down, the parathyroid glands get stimulated to increase the amount of parathyroid hormone released. And the overall effect is to increase plasma calcium concentrations. Okay, and as plasma calcium concentrations increase, we get into, before we get into hypercalcemia, too much calcium, the thyroid C cells can be stimulated to release calcitonin, which then decreases plasma concentrations of calcium. So again, hypercalcemia is actually rare under normal circumstances. So calcitonin doesn't have a large effect under normal circumstances. It really just comes into play when we have extreme circumstances of high calcium levels. And that can be due to cancers and things like that that stimulate bone loss and things like that. So again, calcitonin, mostly in extreme cases, parathyroid hormone in the normal situation. Again, this is a really simplified flow chart. I went through a lot of things of how parathyroid hormone raises plasma calcium and how calcitonin decreases plasma calcium. You guys need to be able to know that and talk about that. Okay. Oh, and so, yeah, I started talking about vitamin D, and then I think I remember I had a slide here. So again, this hormone helps to increase calcium absorption in the intestines. So again, parathyroid hormone can act on the activation of vitamin D, which then would increase calcium absorption at the intestines, and then increases our calcium plasma glucose concentration. And so again, very important to have the right amount of vitamin D. So very important to get, again, most people in the United States have very low levels of vitamin D. So it's important to get that checked out. And if you can't be in the sun, which most of us shouldn't be in the sun for too long, again, you can get it from your diet, leafy greens and things like that, if you don't want to eat dairy products. Phosphate metabolism then is controlled by the same mechanisms that regulate calcium metabolism, again, because phosphate is closely linked to calcium within the bone. So when we control calcium metabolism, or regulate calcium, we actually end up regulating phosphate as well. Okay. And here's an issue with vitamin deficiency. Again, one of the main things we see if people have brittle bones is due to a vitamin D deficiency, right? So brittle bones means maybe you don't have enough calcium in order to build bone. And that might be ultimately because you have low vitamin D. So, so again, with that, with low vitamin D, you don't have the ability to absorb the dietary calcium that came in through the digestive system, right? Through the intestinal absorption. And then therefore, bones will not be properly mineralized because we're trying to keep the calcium in the plasma at the expense of the bones. And so when you have weakened bones in children, that's called rickets. So usually children, when they don't have access to vitamin D and calcium, again, they get those really weakened bones. That's a disease called rickets. In adults, soft and deformed bones is called osteomalacia. And that is